Hello everyone, welcome to Study to Win Education. In this particular video of metrology and quality control, I am going to discuss a topic called process capability. I have already prepared a video on this topic in Hindi language. If you prefer Hindi language, you can watch that. Process capability is very much important topic in metrology and quality control. Process capability topic is mainly based on normal distribution curve. We also call this curve as a ND curve. That means before discussing process capability concept, we should know little bit basic of ND curve. So let me draw a ND curve for you. ND curve. It is a bell-shaped curve. It is symmetric about vertical axis. This is a mean of it. This axis is called as a size deviation, or any deviation you can say. If you are discussing it in mechanical, we generally have a word called size deviation because we measure something in metrology. This axis is frequency. That means frequency of occurrence of that size will be shown in this axis, and this is a generally called as a basic size or a mean about which a data will vary. This normal distribution curve is not only limited to metrology and quality control, it is applicable to various fields. So this particular curve, if I want to talk about it, there is a mean value and this curve will vary about this mean value. It will go and decrease. As we move away from mean value, the frequency of occurrence of that value will go on decreasing. That will be same in this direction also. As we move away from the mean line, the frequency of occurrence of the size at that particular point will be shown by the point on a graph. So frequency of occurrence of a part at this size is only this much, but the frequency of occurrence of a part at this size is very much high. If I add all those frequencies on the graph, these are the various frequencies on the graph. If I add all those frequencies, I will get a number of parts under study. If I add all those frequencies, each and every frequencies, then I'll get a number of parts. Number of parts is equal to area under ND curve. This is the situation. Generally, we will be showing the spread or the deviation from the mean line. I will not call it as a basic, I will call it as a mean. From mean line, we will show the deviation by a term called standard deviation, and we will denote it by sigma. Sigma is a standard deviation, and this is the value 3 sigma up to here. Let's say up to here. This is a size deviation axis. And let's say here it is the second limit 3 sigma. Sigma is called as a standard deviation. Sigma is standard deviation. About a mean, if we go away from a mean, there will be somewhere sigma here. So this is sigma. This is sigma on the other side. Similarly, somewhere here there will be 2 sigma, and so on, that you can understand. So sigma is a parameter which indicate the spread or the deviation from the mean size, and mean is the center of the graph, center of the ND curve. Actually, any data, even if it is in the field of engineering or any data, can only be defined completely using 2 parameters. At least 2 parameters are necessary. One is the central tendency. Another is a spread, or you can call it as a deviation. These 2 parameters are required to completely define a data. Let us take an example so that you will understand very well. I have 2 numbers One is a 5 and then I have second number as a 3. Let's take only these two numbers itself. What is the mean of these two numbers? The mean is 5 plus 3 is 5 plus 3, 8 by 2, 4. 4 is the mean. What is the spread of this number or deviation of this number? This is also called as a range. So what is the range of this number? 5 and 3. Range is 2. So I can define this data using mean and range like this. Let's take one more example of data. If I have a number like 4, or I will have a number like 2 and 6. This is the data. Mean of this data is 6 plus 2, 8 by 2, 4. 4 is the mean. And range of this data is 4. If I only use mean for indicating a data, then we will get confused, because mean of this data is also 4 and mean of this data is also 4. That doesn't mean that this data and this data are same. They are different. But if we specify the range also, then we can come to know the range for this data is 2, but range for this data is 4. That means if we specify data using at least 2 parameters, then we can surely comment on a data. That is why I have used the sentence that data can only be defined using at least 2 parameters. One is the central tendency and another is the spread. Here also this data is defined. One is by the mean and another is by the spread. In this case it is sigma. Sigma indicates the spread of a data. So this is normal distribution curve. In this case, you should have understood that there are some parts which are falling beyond this range. There are some parts, but we are not at all thinking of it. Most of the part are within the 3 sigma minus and 3 sigma plus region. I will call minus for this side, left side of the mean, and plus for right side of the mean. Between minus 3 sigma and plus 3 sigma limits, most of the parts will fall. Most in the sense, almost 99.73% of the parts will fall within this limit. This can happen anyway if the process is normal. This curve will be obtained only if the process is normal. If process has some error, then this curve will not be of this same. It will be some different than this. So we are assuming that our process with which these shafts are manufactured has no error. The manufacturing process of the shaft, manufacturing process with which the shafts are manufactured, and then we have put the data here, various numbers we have put, and we got the frequencies of each number, each size. This everything happened considering the process with which those shafts are manufactured has no error. This process is normal. This is the assumption actually. And then we are defining these limits, and most of the shafts will be falling in this limit, and those shafts will be 99.73%. This is a pre-discussion about the process capability. I'll move towards the topic now. Process capability. There is a machine called machine A. This machine, I have given a shaft to produce 1,000 shafts. I have given to the machine, given to a person to manufacture on this machine, and the requirement for the shaft is it should have a diameter of 50 mm and it should have tolerance of plus minus 0.01 mm. This is the tolerance which I want. A shaft has the person has started producing a shaft on this machine, and then he has taken a measurements of those shafts, and he found that only 500 parts out of it is within the tolerance limit and 500 are rejected. That means it has not matched the tolerance. That means this machine is not suitable for producing part with such a close tolerance. Then the person has increased the tolerance. Person has made it as a plus minus 0.1, and then he found that 800 parts are within the limit and 200 are rejected. Then this is also not accepted, because in 1,000 200 parts are getting rejected. It's not a correct case. it is only loss. So then person has increased again the tolerance to, let's say, 0.3. He has made it as a 0.3 tolerance. And then he found that out of 1000, 99 parts are getting produced. Sorry, 990 parts are getting produced accurately and only 10 parts are getting rejected. So this is pretty good process. The point to tell here is process capability will always define for a machine. It is a indication of a machine. It is an indication of a process. So this is a machine on which this process is going on. This machine is suitable to produce a shaft with a tolerance of plus minus 0.3. It is not suitable for a process which needs a tolerance of 0.1. It is not suitable for a shaft which needs a tolerance greater than or smaller than 0.3. It is not suitable. There will be more rejection than accepted parts. Not more rejection, but unacceptable rejections. 200 is such a high rejection which is not accepted. If it is a tolerance equal to 0.3, more parts are accepted and very less are rejected, which can be afforded by the person. So this machine has a process capability of 0.3. Roughly you can consider this. There is a more detailed discussion on this, but roughly this machine has a process capability of 0.3 because more number of parts it can accept. Almost 99% parts are accepted and only 1% is rejected. That means it is that machine can produce tolerance within 0.3. It is accepted. So 0.3 is a process capability of this machine. Now we will relate this concept with the previous diagram. Here, this is the limit within which the shafts are getting produced. 99.73 parts are getting produced. That means if I consider this is my tolerance, then my process capability is nothing but plus minus 3 sigma, that is 6 sigma. 3 sigma this side, 3 sigma this side. 6 sigma is the deviation. And if this deviation is equal to tolerance in the given case, then I am getting 99.73% of parts within tolerance. So this 6 sigma is nothing but process capability for that machine. 6 sigma is nothing but process capability for that machine. But if I reduce the tolerance, let's suppose this is the tolerance, which exactly matches with the 6 sigma deviation, then this process will produce 99.73% of parts within tolerance. But if I shorten the tolerance, if I make the tolerance smaller, only this much, that means only this is the accepted parts. All those parts are rejected. These are rejected parts in that case. That means more number of parts are rejected. 1%, 2% is allowed, but more number of parts are rejected. Only less, not less, but still this much accepted part is not worth running a factory. There should be less rejection. So this is the case where tolerance is very precise, but the process of a process capability is very high value. So this particular machine is not suitable for manufacturing a tolerance, such a high tolerance, such a precise tolerance. This machine is not useful for producing such a small tolerance. That means process capability for this machine is this value, which can produce a parts having tolerance equal to or greater than this value. This machine can produce the parts which has a tolerance this way. This is the tolerance range, suppose. Then this machine will produce these parts comfortably because this machine has this much deviation. The parts on this machine produced will deviate up to this, and the tolerance the person has asked is up to this much. That means tolerance is wider than the process spread. That means the more number of parts will be accepted. So this is the concept. Now I will draw a separate diagram for this. Let us assume this is our process capability curve. This is a plus minus 3 sigma limit. This is a process mean, and this is a 3 sigma. This is a 3 sigma. And if your design tolerance is something like this, then I can say 99.73% of the parts will be accepted in this particular situation. If the design specifications are this much, then I can say more than 99.73% parts are accepted. And if my design specifications are this much, then I can say very less number of parts are accepted compared to this tolerance and compared to this tolerance. So this particular process is not suitable to produce parts with this tolerance. This process is suitable to produce part with this tolerance. Even with this tolerance also, this process is not suitable because it is cut-to-cut matching. The tolerance is matching with 6 sigma. The tolerance is equal to 6 sigma, which is not accepted because we will get a very precise reading. Very precise. We are at the edge actually. We are at the edge. Process capability will be explained with the parameters or indicated with the parameters called Cp. Cp is a process capability ratio. Process capability ratio. Formula for process capability ratio is nothing but tolerance upon 6 sigma. This is the ratio. When the tolerance is equal to 6 sigma, the Cp value will be equal to 1. For this case, the Cp value, will be less than 1 because tolerance is small and 6 sigma is large. So for this case, the Cp value is less than 1. For this case, Cp value is greater than 1. So this is preferable case. You can use a machine which has a certain process capability. We can use that machine for producing a tolerance higher than that process capability. This ratio should be at least around 1.5. 1.5 is good. 1 is also not accepted. 1 is not accepted. Less than 1 is certainly not accepted. The ratio should be at least equal to 1.5. This is the case. So process capability is designed for a process. It is designed for a machine. It has nothing to do with the tolerance. The process capability has nothing to do with the tolerance. It has to deal with the machine and process. Cp is the process capability index. It is a indication to show the relation between what is required and what we have. It is a ratio of tolerance by 6 sigma. This 6 sigma is a process capability and this tolerance is designer's requirement. Is the particular machine suitable for producing that tolerance or not? This can be identified by looking at the Cp value. This is one case. Let us discuss one more case where this is a normal distribution curve which has some mean and there are two limits. One side there is a 3 sigma, another side there is a 1 more 3 sigma. You must have understood somewhere there is something called as a 6 sigma technology. This 6 sigma is nothing but this 3 sigma plus 3 sigma, that goes to 6 sigma, and this 6 sigma, that 6 sigma comes from the normal distribution curve. We are discussing the same concept. So this is the case where we have a normal distribution curve like this. This will be for some process A. Let's say process A or machine A has normal distribution curve like this. It has a spread of this much, and then I am trying to produce a part with tolerance on this machine, and then I get a tolerance something like this. This is the case where this is the lower limit of tolerance, this is upper limit of tolerance. Now in that case, you cannot use Cp value immediately, because for the point of discussion, consider the tolerance value is equal to 6 sigma value. Here the tolerance value is equal to 6 sigma. With the previous indication of Cp value, we can get the Cp is equal to 1 in this case, because tolerance is equal to process deviation. So we will get Cp is equal to 1. That will give indication that 99% parts will be accepted. 99.73% of the parts will be accepted. But that is not correct, because by looking at the picture itself, you can say this is the lower limit and this is the upper limit. So this is the lower limit of design specification or tolerance. This is the upper limit of design specification or tolerance. Most of the parts are getting ahead of the crossing the upper limit of a design tolerance. That means this is not accepted. So the Cp value, even if it is we are getting it as a 1, but that is not a correct indication. The reason is the mean of a normal distribution curve is not matching with the basic size or design specification mean. Is not matching. There is a difference. In previous case, there it was same, and that is the reason we can easily calculate the Cp value comfortably. But here we need a different factor to indicate the process capability. That is called as a process capability index. Process capability index, which will be designated by Cpk, and we have a formula to calculate Cpk. Let us see the formula. Formula is minimum of x double bar minus lower limit of tolerance divided by 3 sigma, comma, upper limit of tolerance minus x double bar divided by 3 sigma. Cpk is nothing but minimum of these two ratios, where x bar is process mean. Process means this is x bar value, this is x bar value. We will try to relate this formula on the diagram. The formula says minimum of x bar means this value minus lower limit of tolerance means this value, this difference, this much difference, divided by 3 sigma means this much length. So this distance divided by this, we will get a certainly number higher than 1, which is a good indication. But there is a comma, and then there is a second formula. Upper limit of tolerance means this number minus process mean means this much distance, divided by 3 sigma, that means this much distance. This is small, this is large. We will get this ratio less than 1, but we have to choose minimum of this two. So we have to choose this. So process Cpk for this process will be Cpk for this process will be less than 1, which is a correct indication because there are more rejections. So Cpk value should be low. But if we use a Cp factor in this case to indicate the process capability, we will get a wrong result because Cp is 1 in this case because 6 sigma and tolerance are matching. But actually Cp is not equal to 1 also, it is less than 1. If we use Cpk, then we are getting the correct indication. That means bottom line is, if the design specification mean and process mean of a normal distribution curve are matching, then you can use Cp. If design mean and process capability, normal distribution mean are not matching, then you can use Cpk. Before concluding the topic, let us have an example first, a numerical on process capability. Suppose a design specification or a tolerance required is a shaft with a 9 mm diameter has a tolerance of 0.5 plus or minus 0.5. We have a process mean x double bar equal to 8.8 and then we have standard deviation equal to 0.10. These all values can be calculated by so much of statistical analysis. That means we have to take a machine and produce a thousands numbers of parts on it. We have to measure it, then we have to plot a normal distribution curve, a frequency distribution curve, we have to make a ND curve, and then we will get these numbers sigma and x bar and so on. For this case, we have directly given a x double bar, we have given a sigma, we have design spec. What is the mean value of design specification? Mean value is 9 because it varies from minus 5.5 to plus 5. The process mean is 8.8. Clearly, the design specification mean and process mean doesn't match. That means CP will not work in this case. We have to use Cpk. So Cpk formula we know, minimum of x double bar, that means 8.8 minus lower specification limit, that is 8.5, divided by 3 sigma, that is 3 into 0.12, comma upper specification limit, that means 9.5, minus process mean, that is 8.8, divided by again 3 sigma. Minimum of these two will give you a Cp value. Cp. Calculate this, then calculate this. Minimum of these two will be Cp value. Cpk value. If I calculate, I get it as a 0.83. So for this particular design specification, I am getting Cpk value equal to 0.83, which is less than 1. That means to produce a part with a 9 plus minus 0.5 tolerance, a machine with this parameter is not suitable. I should not use this machine to produce this design specifications. Most of the parts are rejected, or the process is not economical because I am getting Cpk value less than 1. I should get Cpk values. I should get at least 1.5. 2 is best, but at least I should get above 1.25. Around 1.5 I should get these values. Then only the machine can be used for discussion. The machine can be used for production of the part. Otherwise, it will produce more rejected parts and the process will not be economical. The discussion about the process capability is over. If you have liked this lecture, please hit the like button, share it with your friends, and if you are not subscribed the channel, please subscribe the channel. Thanks for watching the video. Have a great day. Thank you.